So we're doing another example of differentiation from first principles. So finding the formulas for derivatives of functions whose formulas we know we're given. And in this case, we'll try and find an expression for the value of the gradient of the function y equals sine of x. So we'll try to do this. Find f prime of x, so the derivative of sine of x, from first principle, so using the same method that we just derived. Remember this alternative notation, because I will use this interchangeably. So this is what we're trying to find, okay? And this example will also show you that sometimes differentiation from first principles requires a little bit more knowledge than is required from you at the level of high school or IB maths at least. And that's because of the fact that we deal with limits, yeah? And limits are a bit abstract, so probably that's why they do not put too much pressure on limits in the IB course. But we can use some standard limits, accept them, or sort of I can show you intuitively why some limits are equal what they are, in order to find the derivative, say, of sine of x. So let's bring back the expression for the derivative of f of x in its general form that we derived using this diagram. So this is the gradient between point A and point B, which is the difference in the y coordinates of these 2 points divided by the difference in the x coordinates. When we're trying to make the difference between the x coordinates of these 2 points become 0. That's what this says. So we're essentially going to use this formula now. Let's see where it takes us. So our function f is now sine. So we first have sine of x plus h. And that's this. And now what can we do with this expression? Let's try whatever we can. And what is indeed part of your curriculum is the ability to convert this using trig identity, so compound angle identity. You should probably remember this, but you do have this in the formula booklet anyways. So again, this is in the formula booklet, and this is basically compound angle identity for sine. So now we're going to apply this in our expression. So our A is the x and our B is the letter h here. And remember about this bit as well. All divided by h. We can simplify a bit because we can notice brackets here for clarity. We can notice that we have sine of x here and sine of x in this term as well. So we will put these two together and factor sine of x out. And let's now split it into 2 fractions instead of 1. So this separately and this term separately as well. And the limits add. Now we just need to realize that because what we're doing with the limit, with the idea of the limit, we're trying to make h approach 0. Nothing really changes with the x, with the value of x. So we can bring these things to the front of the limits. And now there isn't much more we can do algebraically here with the knowledge or with what is required from you to know on the IB maths level. However, we can use the fact that these limits here are so-called standard limits. So we can basically use the knowledge of their values. If out of curiosity you're interested, I'll just show you how you can think of the value of this limit, for example. But for now, I'm just telling you the value of this limit is 0. and the value of this limit is 1. So if this is 0, then this term disappears completely. If this is 1, then all we're left with is cos x. And you can double check with the formula booklet whether cos x is indeed the derivative of sine of x. And you will see that that is true. And what's more, because you've done trigonometry already, I'm assuming, do draw the function sine of x in red and the function cosine of x in green, and try to follow these graphs and to do the exercise that we did with the visual intuition of derivatives to basically justify to yourself that this makes total sense. I'll put the diagrams, put the graphs here in the PDF for you as well to look at. And now, so that you're not completely disappointed with just having to take some things for granted as a fact, I'll just try to show you a bit why the value of this expression should indeed be 1. Again, it's going to be a visual explanation just for some extra understanding. So if you look at the function of sine of x, if you zoom closer into what is happening around x equals 0, because we're trying to make x approach 0, right? So we're trying to worry about what's happening, how this function is behaving when we're close to x equals 0. And I've drawn two functions here, both sine of x, so our numerator, and our denominator, so basically just a y equals x. And you can see how near 0 they pretty much overlap. They behave the same. Maybe you've basically come across situations when you were told that you can make an approximation of sine of x being equal to x for small values of x. That's indeed the case. You can see why that is. It's because sine of x does behave pretty much like a straight line of greater than 1, so y equals x, when we are plugging in very small, very tiny values into this function, into the sine. And if we have something that behaves like y equals x, and then we're dividing by a function y equals x, then it feels natural to get 1, because if we're dividing two things that are the same by one another, we get 1. So you can use this form of visual intuition to justify some limits, although this is not the professional way to do it, and you're also not required to do it professionally at all. You're not even required to remember this, but it is worth to actually know this particular limit. That is quite popular, and you will use this a lot in the future.